Okay guys, welcome to Quantum Complexity Theory. This is a master's level course at Paderborn University for the winter semester 2020-2021. So before I start, let me just be clear that this is going to be a course that's kind of intermediate difficulty, meaning that I'll try and cover a balance of more introductory concepts and more advanced concepts, right? So you're going to get a taste of both. If you're really looking for a very introductory course, then I recommend you go have a look at our Introduction to Quantum Computation course, which has its own lectures and videos. I'll show you kind of how to get there later when I go over the logistics for the present course. Okay, so with that said, today really the topic is going to be a classical complexity review. Before I do that, of course, I need to do two things. Number one, I need to, of course, motivate the course for you, okay? And number two, we'll go over some logistics for the course itself, okay, like the course website and how it's going to function. Okay, so let me start with the motivation, and again, I'm going to use a whiteboard. I'm going to try and make this as much like a real classroom experience as possible. Okay, that means I'm going to have my course notes, which you can find on the course website, which I'll show you in a second. I'm just going to be going according to the course notes and writing things on the board. And the start of every lecture is demarcated by a quote, typically that has to do with the content of that lecture. And the one I like to use to start out this course is by Alan Kay, and it reads as follows. Okay, it says, "The future is not laid out on a track. It is something that we can decide, and to the extent that we do not violate any known laws of the universe, we can probably make it work the way we want to." Okay? And in a sense, this is really what this course is about. In a nutshell, like, it's that quote, which is that we are interested about the fine interplay between computing and nature. Okay, what does computing say about the limits of nature, and what do the limits of nature say about the limits of computing? Okay? So, I can say a bit more. I'm just going to kind of go through the introduction section now, right? Which is section 1 of the course notes. So, of course, in complexity theory, we can ask all sorts of questions, right? I mean, the basic question, of course, we're interested in is what quantum computational resources are required to solve certain tasks, okay? So, the tasks involved might be classical problems, like maybe you're given a system of linear equations and you want to solve that, okay? Or they might be, genuinely quantum problems, meaning maybe you want to simulate a quantum system on a quantum computer, okay, like some system of atoms, let's say. And when we do this, of course, we're going to see various complexity classes show up, right? So, of course, we'll see things like quantum analogs of P and NP, but we'll also see some more kind of unexpected classes like QMA2, which seems to have no classical analog as far as we're aware. Okay? And as I said, the key point is we're going to ask, what does nature allow us to do or not to do when it comes to computing? Okay, so the very first step in any journey, any complicated journey, including this one, should always be, why am I undertaking this journey, right? It's not going to be easy. It's going to take a lot of, blood, sweat, and tears, if you will. So what is the payoff, and why is quantum complexity theory interesting? Okay, so I'm going to give you kind of arguably the most famous reason for this, quote unquote. If you've attended our Introduction to Quantum Computing course, or you know anything about quantum computing, you probably already know this reason. But technically speaking, it is the most famous, so I'll say it. It is the one that has to do with Schwarz factoring algorithm, right? So, every day, millions of online shoppers, they, put their credit card information into online websites to purchase things, and the safety of your information when you do this is more or less, quote unquote, guaranteed by crypto systems like RSA, okay? And RSA is secure, assuming that the so-called factoring problem, which we'll define today, I think we'll define today at least, is hard. Meaning that we don't believe a classical computer can solve large enough instances of the factoring problem efficiently. Of course, the problem with this is that we also don't have any proof that factoring is actually hard, right? We can't prove, for example, that it's NP hard, okay? And in 1994, Peter Shor gave this now very famous result, which kind of threaded the needle and said that, okay, even though classically we don't know how to solve this factoring problem, we can actually solve it if we can build a large enough scale quantum computer. We can solve it efficiently, okay? And this, of course, means that if we could build large enough scale quantum computers, then, crypto systems like RSA, which are, among the most commonly used in practice today, would be completely broken, okay? And now, from the perspective of complexity theory, this is already starting to tell us about the interplay between nature and computing, right? Because now we're kind of left with three, what are the implications of Schwarz algorithm, right? So maybe I'll, write a little bit here, right? What are the implications of Schwarz algorithm? Right, so there are at least three possibilities. Yeah, one of them is that we might think of Schwarz algorithm as evidence that quantum computers can do it. So therefore, it should probably also be the case that classical computers could do it too. Right. So maybe this so-called factoring problem is actually in P. Maybe we just haven't been clever enough. Okay. I'll define P later today. Okay, but generally speaking, let me be clear that throughout this course, I'm going to assume some background and familiarity with both classical complexity theory, though we will review it very quickly today, and quantum computation, which again we'll also review in the next lecture. Okay, so the first two lectures, for that reason, we'll go through it a little bit quicker than usual. Anyway, okay, so maybe that's what Schwarz factoring algorithm, we should think of it as evidence that really we've kind of missed something simpler in the classical setting. Or maybe quantum computers are able to solve not just factoring, but they can solve really hard, quote-unquote, problems, such as NP-complete problems. Okay, we'll define that again, or remind you what that means today. Okay, and finally, maybe it's the case that none of these two cases hold above, but that quantum computers can solve intermediate difficulty problems. Okay, and factoring is a perfect example of this. Graph isomorphism is another famous example where you have a problem which is not known to be NP, but we also don't know how to show it's NP hard. Okay, so we don't know which of these possibilities hold. Okay, however, what we can say is that the fact that Schwarz algorithm exists means that we're at a very exciting crossroads in complexity theory. Okay, and one of these three statements must be false, and I'll say more about this towards the end. One of these three is false, and we don't really know which one. And this is what I'll refer to kind of as the crossroads we've arrived at in the field. Okay, number one is that something called the extended Church-Turing thesis is false. Church-Turing thesis is false. All right, number two is that factor is not in P. And, well, number three, I'll let you think about this. Well, okay, let me fill it in for now, maybe. And we'll go a bit more into depth later. So large-scale universal quantum computers, QC will typically mean quantum computers in this course, cannot be built. Okay, so at least at a high level, we're kind of sitting at this crossroads, right? We know a Schwarz factoring algorithm exists, so in theory, if I could build a large enough scale quantum computer, I could solve the factoring problem. And so later on, we'll see that one of these three things are basically at odds with each other. Okay, so the extended Church-Turing thesis, which is a generalization of the standard Church-Turing thesis, which I'll define today, right, must be false. Okay, or one of these, I always get a little bit confused because I always write this in a double negative, right? One of them is false, meaning that, that's my confusion right here. This should be true. Okay, so either the extended Church-Turing thesis is actually going to be false, okay, or factoring is actually going to be in P, or it must be the case that large-scale quantum computers just cannot be built. Okay, one of these three has to be true false. And this is not an entirely rigorous statement. And again, when we revisit this at the end of this lecture, I'll explain why. Okay, but the point is that we're at an exciting crossroads, and to make sense of that crossroads, I'll need to go through the review of classical complexity theory today. Now, what I do want to mention is that regardless of all this stuff, and regardless of the big hullabaloo around Schwarz algorithm, it's not entirely surprising that quantum computers can outperform classical ones, okay? And the reason why I say this is because, long before Schwarz algorithm, it was already believed, very difficult for classical computers to simulate quantum systems, There's this inherently exponential overhead, right? Just to write down the description of a quantum state on n qubits, remember, requires 2 to the power n bits of information. And also already as early as the 1970s, people like Stephen Wiesner were already proposing notions of things like quantum money, which were intended to be secure against any sort of, like, you can't copy these quantum money states if you believe the laws of quantum mechanics. Okay, and this turns out to be correct, assuming you model your notion of access to these quantum states and verification of them correctly. Okay, so the point of all this discussion is that the question, what quantum computational resources are required to solve certain tasks, indeed seems to be a very interesting question, and it has even an impact on our everyday lives in terms of things like cryptography and security of things like RSA. Okay, so that's all I want to say about motivation. Let me tell you a bit about the scope of the course. Okay, so we're going to be talking about quantum complexity theory, very strictly construed. Certainly the field is far too large. We cannot cover the entire thing in one lecture. What I'll try and do is, every time I teach this course, I'll try and swap out 2 of the more advanced topics for 2 kind of more different advanced topics, maybe based on more recent results. And so again, we'll try and balance the course. So we'll see a mix of kind of more introductory kind of quantum complexity theory versus more advanced topics. And along the way, we'll see some mathematical frameworks introduced, such as semi-definite programming, multiplicative weights, and these are all just very nice to know in and of themselves, right? So even if you never take quantum computation again, you're going to strengthen your linear algebra background, and you'll learn things like semi-definite programming, which has uses beyond quantum complexity theory. So there are many kind of topics we won't be able to cover in this course. I've listed a bunch of them here. Maybe I won't go through them here. You can revert to the course notes. What I do want to say is that, some additional resources, in case you want to, supplement these course notes with anything else, these videos, I certainly encourage you to do that. So here's additional resources, I should say. Okay, so here they are. So the main one is the complexity zoo, right? So I don't think any discussion of complexity theory is, complete without mentioning this zoo. Right, so you can Google for it. The link is in the notes, but you can certainly just Google complexity zoo. You'll find it. So this is just basically like a website that has a giant listing of currently, as of this morning, 545 complexity classes and counting. Okay, and has a little bit of information about each. So you can always look up complexity classes very quickly there. There are other surveys that I do want to mention that may be useful. These are in the course notes. So there's a survey by Aharonov and Nave from 2002 on quantum NP. There's a survey by John Watrous from 2008 called Quantum Complexity Theory. There's a survey by Bukatz on QMA complete problems listed here. And finally, there's a survey co-authored with Yishen Huang, Zeph Landau, and Sangwoo Shin from 2015 on quantum Hamiltonian complexity, which is kind of the subset of quantum complexity theory, which deals with quantum constraint satisfaction problems. Okay, so all those links are in here. I'm not going to spend the time to write them down here. You could always go look them up in the course notes. Okay, so in terms of prereqs, again, we're going to need a bit of classical complexity theory and quantum computing, which I mentioned we'll go over briefly today, but I am going to assume some familiarity with those topics before we begin. Okay, so that's all I want to say about intro. Let's take a moment to talk about logistics, okay, course logistics. So everything about the course, basically, if you are registered for this course at Paderborn University, all the communication will happen through the Panda system. Okay, so do make sure you're registered and so you can receive those messages. And how do you find the course website? I mean, so just go to Google, for example, just put in my name, and just click on, I guess, the one that refers to our lab over here. And so this is just the general web page for our lab if you're interested in our research or anything like this. And so what you want to do is you want to go to the teaching link over here. So click on that. And so here we list current and past courses. So here you'll see, for example, this term we're offering, of course, quantum complexity theory. That's the present course. There's also an advanced seminar on quantum computation being taught. And regarding that intro to quantum computation course, which I mentioned, here it is. That's this one over here. So if you want to view that past course, the the lectures, the video lectures for that, et cetera, those are all here. So today we're just going to click on quantum complexity theory. And here's the basic website for the course. So as I mentioned, all correspondence will be through Panda. The lectures in theory, of course, are supposed to be during these times, but as you know, they're going to be via this asynchronous online format, meaning that I'm just going to record these lectures and they're going to get posted to YouTube and links publicly posted. Tutorials. Tutorials are going to happen every week as well, but only starting in I believe this should be the 3rd week. And these are going to be synchronous, meaning that they're going to be live. Okay, so this will be the only opportunity in the class. Well, I shouldn't say that. But let's say the primary opportunity in the class for students to interact with the instructor, okay, in a live fashion. Okay, this is of course all happening remote due to COVID. And so those will take place in Big Blue Button. So I'll give you the information for that closer to the first tutorial. But let me be clear, those tutorials are going to be private, right? So those are not going to be publicly broadcast in any sense, and they will only be available to registered students at the university who are in the course, and that's of course for privacy reasons. Okay, so I do not want to get into the mess of asking students to sign their soul away so that we can post this online. It's supposed to be a private space where students can freely ask questions in terms of the content. Okay, so just a heads up, tutorials will typically be a chance to go over the lecture material, to ask any questions you might have, and also to go over, of course, the assignments. So suggested textbooks and references, here's more. I guess this link should be updated, technically speaking. There's a more recent offering of this course. And, this course that I just mentioned previously, it has, kind of a full set of lecture notes as well. So you can refer to that. That's a purely introductory course. Kind of the standard textbook, the Bible on the field, remains very much Nielsen and Chuang. So, you don't necessarily have to have this book around, but it's kind of like a textbook that everybody has as a reference. You don't need it for this course, strictly speaking, but again, it's the standard reference. And here are some of the other references I'll mention. Probably the most recent one of these that I do like to kind of plug, if you will, is Ronald's course notes, which I think are also excellent. And this is fairly broad. It assumes a little bit more background, I think, than the intro to quantum courses that I have up here, but nevertheless, they also cover a set of topics which I do not cover, and so Ronald, I think, is an excellent teacher. You have nothing to lose by looking at these. Okay, so I strongly recommend those as well. Exams will probably be take-home written. Don't quote me on that. We might also do oral. It really depends on how the course develops and the number of registered students and so forth. But it's a bit difficult to give a good exam for this course without having you write things down. And in the COVID era, that's a bit hard to do online, right? I would have to get each of the students to have their own writing tablets, and I don't want to assume that. Okay, so contact information, that's my email. Okay, if you're interested in following my Twitter feed, that's where it is. And typically what I do on Twitter is I'll post out kind of all sorts of opportunities that I run across, like workshops that might be taking place or funding opportunities for students and so forth. So if you want to receive that information, this is usually within the broad realm of theoretical computer science. Feel free to sign up there. My office is here, but as you know, typically most things are online this semester, so that's probably how things will run. But strictly speaking, I do have office hours as long as they're kind of allowed according to the COVID guidelines on campus. Good, so that's the basic webpage. Just a brief look at syllabus and reading. So all course notes will get posted here on this link. So right now you'll see the current lecture notes for today. If you click on this, it should pull up the course lecture notes, wherever they went. Where did they go? One more time. Sorry. As you can tell, I'm a Google Chrome boy. Okay, yes. But I do remember how Firefox works. Okay, there you go. So this is just, for example, what the lecture notes look like, right? So this is today's lecture notes. Here's that quote we started with. And once the course is completed and I've posted all the lecture notes, I'll compile them into all one giant document and release that as one big thing as well. Okay, but for now I'll just release them week by week. Okay, so this is roughly speaking what they'll look like. And let me be clear that there will be exercises kind of interspersed between the lecture content, so like this and this and this. Those are things, of course, we could review in tutorial. I strongly urge you to do the exercise. Okay. Lesson 101, right? When you're doing anything complicated, if you don't do the exercises, you will not understand the content, right? You'll think you understand it, but when it actually comes down to doing the content, right, you'll realize that there's a lot you're missing, okay? So I really strongly encourage you to do the exercises. Okay, so those are the course notes. Let me close that. Syllabus. If I ever update the syllabus, which is entirely possible, here it is, basically. Let me click on it. Oh yeah, that's right. Good. So here's the syllabus. Most of this information is kind of repeated from on the course webpage. Just a brief preview of some of the major topics we'll cover. So today will be a review of classical complexity theory. Next class we'll review the basic quantum circuit model. And after that we'll start kind of new material. The quantum version of P. A BQP complete problem, which is this well-known algorithm of solving linear systems of equations on a quantum computer. Then we'll talk about quantum NP, right, and a quantum analog of the Cook-Levin theorem. And then we'll see that there's more than one analog of quantum NP, and so we'll talk about other classes like quantum classical NP, if you will, quantum interactive proofs, and then we have some time for some more advanced topics, and we'll see how the semester goes, and I'll try and cover maybe some of these things or some other things depending on kind of what's the latest and greatest in the field in some sense and what seems to make sense. Okay. Class schedule you are now well aware of, and I've sort of mentioned. In terms of the grading scheme, I'm not a huge fan of discretizing grading schemes, the percentile into these fixed kind of blocks like 1,0 or 1,3, but that's the way it is, and that's the way we'll do it. This is the grading scheme we are offering in this course. Okay, so anything from 95% to 100% inclusive will be 1,0. Okay. What I will probably do at the end of the course. This is not mentioned on the course webpage, so let me take a moment to stress this. This kind of came up on the fly the last time we offered this course because there was a request for it, more or less. And I do want to offer it moving forward. So if you prefer not to do an exam, but instead you want to kind of do some research, I'm very happy to support that. I can base your final grade on the research rather than the exam. Okay? So that the guidelines for that will be posted later in the term. Let me clarify, of course, that actually we'll see this in a second, but there will also be homework for this course, but the homework will only be graded for completeness. Okay, so that means that after each homework is collected, I'm going to just release the solutions and expect you to act like big boys and girls, to look up the solutions yourself and see where you made mistakes and where you can improve. This is also important because you can kind of see what we're looking for in terms of, quote-unquote quality of solutions, like what is the expected writing style and the amount of conciseness we're looking for, if you will. By the way, writing good scientific text may seem like an easy skill, but it's one of those things that takes a very long time to pick up. So don't be discouraged if at first you find your solutions a lot more differing a lot from the expected solutions. Let's say, of course, you don't need to reproduce the expected solutions, but it is good to try and be precise and concise, and not bloat your solutions too much. And of course, to be formal. Okay, so for the homework, of course, there will be benefits to doing it. Other than obviously, you should absolutely do the homework if you want to understand the material. There's a very strong correlation between people who pass the course, who do well in the course, and those who do the homeworks, right? I would argue that's a causal correlation, but of course, correlation does not imply causation, that's just experience though, okay? So the name of the game is that if you complete at least 60% of the homeworks, and then remember, I'm just gonna grade you completed or not completed, basically, you'll get 1 step bonus in your final grade, and if you do at least 90% of the homeworks, you'll get 2 steps bonus. Okay, so that's my formal nudge to kind of do the homeworks, but of course you should do them anyway. Okay, that's all I want to say about syllabus. One thing that I did not mention, and it's not mentioned here, is that, I don't think it's here, is it? No, okay. So there will be a course, there is a course kind of news group or discussion board that is on Panda. Okay, so if you want to ask questions for the course, either to me or to your fellow students, I always recommend you go there first because, anybody can answer there. I strongly urge students to also answer their fellow students' questions there. That's probably the fastest way to get an answer, especially if it's something, technical about course content. It gives you a chance to discuss among yourselves and learn that way. Okay? So, and if that doesn't work, then you don't get an answer then of course you're welcome to email me here. Okay, assignments. Assignments will typically be due, basically, Tuesdays are tutorial day. Remember, that's live, so typically I'll expect the assignments to be due right before tutorial starts. And the idea is, of course, then that we could review the assignment solutions together in the tutorial. Of course, we'll discuss them in the tutorial. All assignments will be handed in through Panda, and I'll distribute your grades through Panda, of course. But again, remember the grades are only in terms of the semester end bonus. And let me be clear that the submission format that we prefer is PDF, just because it looks like right on any machine and it's easy to read. I strongly, strongly encourage you, especially at a master's level course, to produce your solutions via LaTeX. Okay, and what I'll do is for each assignment, I'll release a LaTeX template file that you could basically start with to write code your solutions, just to save you time. If you're doing any sort of work in theoretical computer science, not necessarily quantum, moving forward, you're almost certainly going to be working with LaTeX. So it's worth getting comfortable with right now. That's it. This link just takes us back to our research webpage. That's it. Okay, so that's the course website. All announcements will come here. So here's kind of the first announcement, but they'll also be posted to Panda if you prefer. Okay, so that's it for motivation, introduction to the course, and logistics. And now we can start the actual content for the course. Okay, so let's move next to the actual content of the course. Okay, and we're just going to very briefly start by setting up notation. Okay, so this is section 2 of the notes. Notation. So just some very standard notation I'm going to use kind of throughout, but I want to make sure everybody's on the same page. Clearly, as you can tell, I don't know how to draw straight lines. That's going to happen quite often in this course. So these are the main symbols we're going to be interested in, right? In terms of sets of numbers, right? Oops, that is totally not how it's done. Okay, so remember these are the natural numbers. These are the reals. These are the integers. And these are the complex numbers. Okay, so that's the notation we're going to be using. Normally I'm going to, when I talk about the natural numbers, I'm going to assume that it includes 0 in our definition. Okay, unless otherwise stated. And a lot of times I'll talk about, z plus or let's say r plus. Okay, and these are just going to be non-negative. Okay, so for example, non-negative integers, non-negative real numbers, and so forth. Okay, the set of all n-bit strings is, of course, just going to be 0, 1 to the n. Okay, and something that's slightly less standard, let's say, is that if I say this thing, absolute value of x, I'm going to overload in this course the meaning of the absolute value, so I want to be clear about this, right? So this has two possible definitions. So if x is a complex number, okay, then the absolute value means the magnitude of this number, right? The absolute value of x is, so normally, of course, well, let me just give you the strict definition, right? If x is complex, then it's the square root of x star x, okay? And if x is a string, on the other hand, so in other words, if I write it this way, okay, then I'm going to think of absolute value of x as denoting the length of the string. Then the length of x, in this particular case, for example, is n, right? Because there are n symbols in it. Okay, so it's just going to be context dependent. I think it should be clear from the context. I'm going to use the notation, these square brackets of n to denote the set 1 up to n. Okay, just to save myself from having to write a few symbols over and over again. And finally, if I do this thing, it means a definition. Okay, so if I do an equal sign with the colon before it, this is fairly standard. Okay, that's it, basic notation. Okay, so now we can start on the real content, if you will, for today, which is just a review, a quick review, of course, of classical complexity theory. And of course, I'm going to sort of frame it in a lens that will be appropriate for us to build on in the future, okay, in the next coming lectures. Classical complexity theory, section 3 of the notes. Okay. Okay, so what we want to talk about is, of course, the complexity classes P and NP, right? That's going to be the starting point of any discussion of complexity theory. And in order to do this, of course, first I need to define, or I need to remind you of the definition of a Turing machine, okay? And let me be clear that, typically in quantum complexity theory, one does not work with quantum Turing machines, though, the concept is well defined and it does exist. Typically, we work in something called the quantum circuit model. But there's an important reason why we cover Turing machines now in this first lecture, and it's because later in the next lecture when we discuss classes like, say, BQP, we have to define the notion of a uniformly generated family of quantum circuits, and for that we need to have the notion of a Turing machine under our belts. Okay, so everything always in some sense boils down to Turing machines under the hood, right? Okay, so let's start with Turing machines, which, I'm going to write down a definition for, but I'm really not going to spend much time on it. There's quite a lot of details you can jump into if you want to, but, for our intents and purposes, what matters is kind of the intuitive definition more than playing with the particular sets that I'm about to put down. Okay, so what were Turing machines, just as a brief reminder, right? If you want to study anything from a rigorous perspective, okay, especially things, having to do with, physics, life, right? You need to define a mathematical sandbox, a model in which you can play, okay, kind of a standardized model, right? And so you need to define, in other words, what does it mean to compute? What device are we talking about? Are we working on? The Turing machine is that device, okay? It's a theoretical model. Remember, you could never actually build a real Turing machine because, it has an infinitely long tape, but, it's a theoretical model and it has played a very important role. It was first proposed in 1936 by Alan Turing. Okay. And, as you probably already know, it's a remarkably simple model in hindsight. By the way, I'll talk more briefly about the significance of Turing machines in a second, but first let's just define them. But the idea is very simple, right? There's kind of like a brain or a control unit that kind of makes the decisions. And then there's like an infinitely large memory or a tape onto which you get to write things and read things. That's kind of like your storage, okay? And of course, the interaction between the brain and the tape is via some head that kind of moves around and reads, okay? So let me just kind of give you a formal definition, right? This is definition 1 in the notes of a Turing machine, or just a TM for short. And, I'll write down some set notation and things like this, but, this is really kind of, I'll go through it quickly. We're not going to play much with the set notation. It's just, I don't want to wave my hands too much. I want you to see something, pseudo-rigorous, if you will. Okay? So, a Turing machine is what? It's basically a 7-tuple. And so that means that we're going to have 7 sets, or not sets, but 7 objects. So Q, sigma, gamma, delta, Q naught, Q accept, and Q reject. Okay, so there are 7 objects in play. And let me define each of them. Right, we'll start with the set Q. Okay, so to specify a Turing machine, you need to specify these 7 things. So let me briefly remind you what these 7 things are, right? So first you need a finite set of states the Turing machine can be in. Okay, because ultimately it's a state machine, okay, finite state machine. Number 2 is sigma. Okay, so first we did Q, now let's do sigma. So sigma is what? These are going to be basically the symbols which are part of the input is allowed to be written with respect to. Okay, so you're going to write the input with respect to some alphabet. So that's basically sigma. So this is going to be, again, it's a finite set denoting the input alphabet. Okay, so these are the symbols with which the input is going to be written on your tape before the Turing machine starts. Okay, number 3. Let's now do gamma. Gamma is very similar to sigma, except now this is just going to be the general kind of tape alphabet, the workspace alphabet. So again, it's a finite set. And now this is going to be the tape alphabet. Okay, so the reason why we distinguish between these two is because typically the tape alphabet has an additional symbol which the input alphabet does not. And this includes this special blank symbol, right? And the reason why we don't include this in the input alphabet is because usually the blank symbol is used to demarcate the end of the input, basically. Okay? Okay. Good. So now we can talk about the state of our machine. We can talk about what kind of symbols we're allowed to play with. And then, of course, we need to know about the behavior of the machine, and that's fully specified by this function delta. So here's delta. And so let me give you a specification for this, kind of mathematically speaking. So what does delta take in, right? To decide what to do, think about this for a second. The machine wants to kind of think about its current situation and make a decision as to what to do next, right? So in order to do that, it needs two things, right? It's going to read its current state. Okay, so that what it does next, of course, depends on its current state. And it's going to read kind of what's under the head, right? So let me, by the way, sketch this very quickly, right? I'm sure you've seen this picture before, but kind of here's the brain of your machine, right, if you will, that stores the state. And this thing kind of gets a head, right, that accesses this like infinitely long tape full of information. And each one typically will work in binary, so wherever the head is, you can read the symbol under that position, right? So depending on the certain state, and we can read a symbol from the tape alphabet, right? It's going to decide basically what to do next. Okay, so of course it can possibly go to a new state, so there'll be 3 things this thing will output, this function. The transition function, that's what this thing is called. So the transition function. Okay, so of course it will output a new state. And now wherever this head is, right, I can also, overwrite that symbol. So I can output a symbol I'm going to write down. And finally, of course, I can move the head left or right 1 position. Otherwise, I'm always stuck at the same spot. And so therefore, typically, we just write L or R here. Okay, so this means, for example, move the head right 1 cell. Okay, that's kind of a standard definition we'll use. Okay, so the astute, somebody who's paying very careful attention might notice that, over here, I said as input, the symbol you read is coming from gamma, but what about sigma, the input alphabet? And the reason why I can put here this capital gamma without loss generality is because, technically speaking, I haven't written it down, but sigma is always assumed to be contained in gamma. Okay, so whatever you could write on the tape in general should of course include whatever is allowed to be in the input, plus additional symbols like this blank symbol, for example. Okay, so that's basically the behavior of our machine. Okay, so now we know everything about kind of the behavior of the machine. Now I need to tell you about kind of what are the special states the machine can be in, kind of when it starts and when it ends. So the start state is Q0. So this is in Q. Okay. And this is the start state of the Turing machine. So when you have the input written on the tape, a bunch of blank symbols after it, and then you have this machine up here. The head, the brain is in the start state Q0. And then of course I want to ask, when does this thing terminate? Okay, and what does it do when it terminates? And we're always going to assume in this course, well, for the most part, we're going to assume these Turing machines output a single bit, which means I'm going to end in either a state Q accept, that's this one, or Q reject, which will be this one. Okay, and Q accept will be analogous to saying we output 1, let's say, and Q reject will be like saying we output 0. Okay, so let's do Q accept. This is the accepting. So let me be clear, the accept and halt state. Okay, so by which I mean, when you enter Q accept, we assume that the Turing machine halts immediately and it outputs accept. And likewise, Q reject is the same idea, except now it's going to be the reject and halt state of the Turing machine. Okay? So, this is a standard definition. And, I don't want to go into any more depth than this. I just want to give you a sense of, what's kind of under the hood when we say, let's formally define a Turing machine. This is how you do it. Okay? Okay. So, now that we have a formal definition of a Turing machine in hand, right? We have a notion of, what is one step of a computation? We can formally define this. What is one step of a computation? How do we define cost, right? If we're talking about the number of steps a Turing machine takes to solve a problem, right? So it'll be three things, right? One step contains three things, right? So number one, we read the current symbol under the head. Okay. Then we update the state of the Turing machine itself. Okay. And finally, of course, we're able to overwrite the current symbol and move the head. So write symbol to a current cell, and we can move the head left or right one cell. Okay? That's it. Those four together constitute one step of a computation on a Turing machine. Okay. So just some very basics, right? Before this computation begins, right? We assume that kind of the input is on the tape and followed by an infinite number of blank symbols, okay? And once the machine starts, it's going to execute a sequence of computation steps according to its transition function, right? That was this delta over here, right? And once it enters the accept or the reject state, that's these guys, right? We're gonna assume it halts, okay, and accepts or rejects. And we'll also assume that when the machine does halt and accept or reject, we can also assume at this point that if it wanted to output, let's say, a string in addition to just a bit 0, 1, we can assume that that string is written on the tape and followed by an infinite number of blanks, right? So that's all that's left on the tape, the desired output. That's without loss generality. And finally, of course, let me make a very important point or an observation. So given an input x, right? So a Turing machine need not halt, right? So if you studied Turing machines before, you certainly know this, that in principle, it's possible for a Turing machine to just kind of go on forever. Even though it has only a finite number of states, it still has an infinitely long tape, right? So this could make it kind of go on forever and not halt. Okay, so exercise 2 in the notes, which I won't do in this lecture, gives you an example so that you kind of get comfortable with Turing machines. Again, refresh your memory. It says, given an input string x, sketch how the Turing machine would, output 0 if x contains only zeros, the input string, or if it contains at least 1, 1, then the machine should halt and output 1. Okay, so in other words, you want to compute the OR function of all the input bits. And think about kind of what is the runtime of this thing. Okay? And of course, typically when you're doing this, you want to maintain your sanity, you want to do this in pseudocode, right? So you're not going to obviously write out this full state space queue over here. That's a little bit ridiculous for a more complicated computation like this. But you want to say something like, okay, read the current bit under the current head, and if it's 0, then you just kind of move to the right. If it's 1, for example, then you've found the one you wanted, so you can kind of go to the first cell, up, write down 1, and then erase the rest of the tape and halt and accept. Okay, so that's all I want to say about Turing machines. Again, we're not going to play with Turing machines too much directly in this course, but they are very important. Number one, because you need to understand kind of what's happening under the hood. Okay, when somebody says what is the runtime of something, you need to understand it's typically always ultimately based on Turing machines. And we're going to use them in the next lecture to define the notion of uniformly generated circuit families. Okay? And, just as a heads up, why is that going to be the case? Well, a Turing machine's input can be any size. It can be, it's flexible, right? A Turing machine does not have a fixed input size. A circuit, however, is fixed, right? It's the number of inputs it takes, the input wires it takes are fixed ahead of time. So that's why you need a Turing machine to say, okay, this is the input size I want, so I'll generate a circuit that can take an input of that size. That's ultimately why we're going to need to do this uniform thing, uniform generation. Okay. So having defined Turing machines, let me remind you that typically in classical complexity theory, the main thing we focus on are decision problems, which mean problems to which the answer is yes or no. And to kind of formalize all of this, we kind of super abstract it all in terms of languages. Okay? And so let me remind you how we define a language. It's just going to be a subset L of all strings. Okay, right? And so, there's no particular fixed size of these strings necessarily a priori. Okay? They're all finite length strings. By definition, a string is finite length. But, there's no upper bound on the size of strings that can appear in L. Okay? And so, in a decision problem in this setup is typically the following, right? So you're given a string x, and it's just some n-bit string, right? So, okay, so it has some finite size. And your question is x in L, right? You have to decide yes or no. Is it in this language, in this subset L? And this may look super obscure, right, or abstract, but it properly encodes the definition of, or the idea of a proper decision problem, right? So maybe we're talking about the set of satisfiable 3-sat formula, right? I give you a 3-sat formula and I want to know is it satisfiable or not. And so L could here refer to the string encodings of all satisfiable 3-sat formula, for example, right? So given an input x then would be a 3-sat formula. Is it satisfiable? Does it belong to the set L? Okay, so this is just a very nice, super general way to encode these decision problems in terms of binary strings. Okay. Now, we'll say that a Turing machine decides a language, okay, if basically no matter what input you give me, the Turing machine halts, okay, for all inputs x, the Turing machine halts, that's super important, and accepts or rejects. Okay? So we'll never run forever. Okay? So by the way, of course, let me be clear, accept is if you're in the language, of course. It will reject if x is not in the language. Sorry, let me be, that's of course necessary because I'm talking about, deciding the language L. Okay. Okay. And let me be 100% clear here, right? This notion of decidable says nothing about the time complexity. Okay, so it says nothing about how many steps you need to actually decide this language right now. It's just, can you do it at all? Okay. And the reason why I'm making this point is that, recall that there exist undecidable languages, right? Languages or decision problems where it's just impossible to answer this yes or no question for it in general. Okay, so there exist undecidable I don't quite remember if there's an E here. My notes say there is not. There exist undecidable languages L. Okay, so intuitively that of course just means that there are yes or no problems which no Turing machine can solve in a finite amount of time. Okay, and let me be clear that these undecidable problems certainly do show up in quantum complexity theory as well, but there's a good chance we won't have time to cover those types of results in this course. There's just too much to cover, right? That's the only reason why. Still very interesting. So let me just very briefly go over the two exercises that are next in the course notes. Exercise 3, right? And this one basically talks about the halting problem, right? So remember, the halting problem is you're given as input, an encoding of a Turing machine M. So let me be clear. These angled brackets are just basically the binary encoding of this object. And M is just a Turing machine. So let me do this, Turing machine. And you've got some input X, just some string, right? The question is, does M halt on X? Okay, so remember that this is the halting problem, kind of the most basic question you can ask about a Turing machine. And this is undecidable. So this exercise asks you to prove that a halt is undecidable. This is not necessarily, it's not a very long proof, but it's a clever proof. So you might need to kind of look it up to get some hints if you feel stuck. But if you've studied computability theory or complexity theory before, you've almost certainly seen this. And the reason why I like to mention this is because here we'll see our very first very drastic separation or departure between theory and practice. Okay, so in theory, the halting problem is undecidable, right? But that really crucially uses the idea that we have this infinitely long tape, okay? And in practice, my computer, which I'm recording this lecture, it doesn't have an infinite amount of memory, right? Nothing in the universe is infinite, right? It has a finite amount of memory. And so this is going to ask, on a real life computer. And so think about this as basically like a Turing machine with a truncated tape, right? The tape is finite size, right? So i.e. finite size Turing machine tape is a halt still undecidable. Okay? So think about that, okay? So I've given you slightly more hints in the lecture now that are in the course notes, but this is an important distinction to understand between theory and practice, okay? Now, of course, even if the answer is no, it's not undecidable, or maybe I should say, even if the answer is halt is decidable, it doesn't necessarily mean you can do it efficiently, right? Okay, so let me just take a very brief moment to talk about the significance of Turing machines. Seriously. Okay, got it. Significance, right? So 2 remarks. Okay, so number 1, when you look at this Turing machine model, right, in hindsight, it looks extremely basic, right? And basic as in kind of obvious, right? Most of our modern computers essentially work this way, right? You've got this like the brain, the CPU, right? And then you've kind of got this literally you have a read and write head, right? Which at least until the advent of like solid state drives was certainly the case with, with the physical hard drives, right? That use this, the spinning platter, right? And this arm that literally did this seeks on it, right? So that's no coincidence, right? A lot of the development of modern computers, the way they've been developed was, highly influenced by Turing's ideas, right? So that's why in retrospect it seems kind of obvious. And let me also be clear that, so it really strongly influenced modern computer design, even though it's like such a basic model, right, the Turing machine. Number 2, another reason why it was super important, this notion of a Turing machine is that, in order to prove anything rigorous, you need to, again, formally define, the sandbox in which you're playing. What are the rules you're allowed to apply, and what kind of objects can you play with, right? And so the idea of an algorithm kind of had been floating around since, thousands of years, right? Euclid's algorithm, for example, for computing the greatest common divisor, that's been around since like 300 BC, right? But the formal definition of an algorithm, didn't really kind of materialize until, Turing came around with his Turing machines, for example. And now you could define formally on this machine what it meant to take a finite number of steps to solve some problem, okay, given an input, okay? So it finally gave us a formal definition of an algorithm. And you might think this is kind of a weird and fussy thing to, well, something odd to fuss about. But you should be reminded that around the turn of the century, David Hilbert gave this very famous list of kind of great mathematical challenges for the next century. And some of them involved finding algorithms for things like Diophantine equations, right? Where it was kind of almost expected that an algorithm for this problem should exist. And it wasn't until kind of the notion of algorithm was formalized that you can finally formally prove that no, some of these problems just cannot be solved by a computer, period, right? Assuming, of course, you're working in the Turing machine model, right? And I'll get back to that in a second when we talk about the Church-Turing thesis. So it's very important to formalize things, okay, is the point, so that you can prove things rigorously at this point. Okay, so the second, well, now it's become the third point, but in the notes, it's the second point, is the so-called Church-Turing thesis. Okay, and there's a sense in which the Church-Turing thesis is the thesis on which all of theoretical computer science is based, more or less. Okay, so why do we put so much emphasis on Turing machines, right? The reason is because of this thesis. The thesis basically posits that anything you can do on a model of, like on a mechanical machine, let's say, can be simulated by a Turing machine. Okay, so a little bit more formally, right, slightly more formally, right, if there exists a mechanical process for computing some function f, right? So maybe it's going to be something from n bits to 1 bit, just to give you a sense. Then there exists a Turing machine computing f. Okay. So that's what the Church-Turing thesis basically posits. So in a nutshell, what this is saying, of course, is that if you want to understand the power of computation, right, the only model you have to care about is the Turing machine, nothing else. Okay, that's what it's saying. Okay, now 2 points, right? The first point is that this thing is, well, notice how I didn't write Church-Turing theorem, it's a thesis, right? So this is not a proven theorem. Right? Like nobody knows if this is actually true or not, right? But of course, proving this thesis or disproving it seems like a very, very difficult task. Like it's not clear how in the world you would even go about doing this. Okay? It's certainly, extremely well adopted, right, by the community that this thesis is true. Now, the thesis says nothing about runtime. Okay, so when I say like, okay, there exists a function f, right, such that some mechanical process can compute it, all I'm saying is that there exists a Turing machine that can also compute f, right? It says nothing about how much time that Turing machine takes with respect to how long this mechanical process takes, okay? So this is basically what this captures is decidability, right? If you can decide a language, let's say, using some mechanical process, then you can certainly always do it with a Turing machine. Okay, and that's the basic claim. If we want to talk about runtime, right, and this is what we'll talk about at the end of this lecture, then you want to talk about something called the extended Church-Turing thesis. Church-Turing thesis. And, to be fair, this thesis is much less accepted than the regular thesis. And there's a sense in which it really kind of came to prominence because of Schwarz factoring algorithm that suddenly showed that factoring is in polynomial quantum time. And so kind of this extended version of the thesis came into question. And we'll talk about this at the end of the lecture. Okay, but generally speaking, this the extended thesis is kind of in parallel, is in parallel to Schwarz factoring algorithm. Good. So that's Turing machines, languages, and decision problems. So now that we've got all that basic framework under our belts, we can now define our first two complexity classes, which are P and NP. Okay. So these two complexity classes are arguably the most famous exports of the theory, right? Complexity theory. Okay, so if there's anything you know about the field, it's typically P, NP, and NP completeness. Okay, and that's more or less what we're going to review quickly in the remainder of this lecture. Okay, So roughly speaking, P is going to be the set of problems we can solve efficiently on a computer, meaning in polynomial time. And NP will be the set of problems which, we don't know how to solve them efficiently, but at least if you give me the answer, I can check the answer efficiently. Okay, so in this course, there's going to be an emphasis on rigorous definitions, okay, and good math, if you will. And that means that I'm going to write down a formal definition of P in pretty much all the complexity classes we visit in this course. So let me start with definition 2. P, which stands for polynomial time. Okay, you might also want to say deterministic polynomial time, because NP will be non-deterministic. So again, let me stress that P and NP only talk about decision problems. So we'll say that a language L is in P, right, if there exists a deterministic Turing machine. And let me be clear that in this course, whenever I say the words Turing machine, I always mean deterministic, unless I have explicitly said that I don't mean deterministic. So whenever I write TM, it's deterministic in your head. Okay, and there's a fixed polynomial. R subscript L from the natural numbers to the positive real numbers, such that, okay, so in this course, I'll always use this notation, ST, which means such that. For any input x, right? So this is going to be, say, an n-bit input. M halts in, at most, order, whatever this polynomial was of n steps. Okay, so it runs in time polynomial of the input size. And, okay, so now we have conditions, right? The first condition is completeness. And, or the, in English, the yes case. And this just basically says that if x is in the language we want to accept, so M halts and accepts. 2 is soundness. And this is the no case. So if x is not in the language, M rejects. And that's it. Okay, so that's going to be our definition of P. And note that what we see in here in this definition is that efficient computation for us is going to mean this, right? I mean that your runtime will scale like a polynomial R. Okay, so polynomial time is efficient for this course. Let me be very clear, right? In practice, that's like completely removed from the truth, right? So even an n² time algorithm in practice is, generally speaking, completely unusable, right? I mean, that's not always true. It depends on the hidden constant in front of, in the big O notation, but generally speaking, n² is unusable in practice. You need to have at most something like n times polylogarithmic in n, okay? Kind of my most favorite example of this is the Fourier transform, right? If you want to compute the Fourier transform using brute force, then that takes n² time. But in practice, we don't use the brute force implementation. We use the fast Fourier transform, which takes n log n time, basically. And this makes all the world of difference in terms of something that's completely unusable n² versus something that's kind of already inside pretty much every single gadget you use every day. Anything that processes sound or video, right, uses the Fourier transform, such as your smartphone, for example. Okay, and so that's why this is possible, because you can do it in essentially linear time. But from a theory perspective, anything polynomial time is what we'll consider efficient. And roughly speaking, the intuitive reason for this is because that makes the class kind of robust. We can give reductions between different problems, showing that they're kind of the same complexity and so forth. Okay, and also then the Turing machine model also becomes robust, because then you can simulate kind of this basic model. You can use this very basic model to simulate other models, like maybe two-sided tapes or multiple tapes, or so on and so forth. Okay. Okay. So, just very briefly, exercise 6 asks, are all languages in P decidable? So think about that for a second. I will take a drink of water while you think. Okay, and why or why not? Well, I'm telling you that on all inputs, this thing halts. And I'm telling you something stronger, right? I'm telling you that it halts in a polynomial number of steps. So certainly it's decidable, right? Decidable just meant that on any input you halted and you accepted or rejected, regardless of how long it took, right? So it's even a weaker definition. Now, what is a little bit more subtle, but is, I think, very important to understand, is exercise 7. Can the choice of RL, this polynomial here, right, this guy over here, can it depend on the input, x? This is a very, very important question, okay? So notice how the way of in theoretical computer science, and certainly in math in general, the order of quantifiers is very, very important, the way you write things, right? So here what I'm saying is that first I have an existential quantifier right here, right? There exists a deterministic Turing machine and there exists a polynomial RL, right? So I first fix those two. Then such that for all inputs, now I have a for all quantifier, a universal one, m halts at most, blah, 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 okay? So I first fixed the polynomial before I've talked about inputs. So now I'm asking what happens, is this order important? Can the polynomial depend on the particular input, right? So think about that for a second. The answer is obviously not yes, otherwise I wouldn't ask it. Think about why, if you did that, then this class P isn't really going to be well defined anymore. Okay, so let me be clear that if you really want to master a topic, these kind of edge cases are typically where once you understand those, that's when you really start to understand something in depth. Okay, so that's why I really stress thinking about these exercises. Good. So let me give you a simple example of a problem in P, right? A problem that you certainly have known since you're, what, grade 2 or grade 3, I think, right? So here's a problem in P, right? And I do this, number one, because you certainly know of this problem, so it's familiar, but number two, it shows you how you can kind of phrase non-decision problems into decision problems, okay? So integer multiply, okay, integer multiplication. So normally in grade 2 or 3, you learn that, given two integers, you can multiply to get their product. That's not a decision problem, right? The answer is not 0, 1, so let me write it as a decision problem. So you're given as input two numbers. Let's just assume they're integers. And I want to turn this into a decision problem, so I need a threshold, t, also in the integers. And the question is the product xy at most t? Okay. And so now this is a decision problem. I'm going to assume all the inputs are specified in binary here. And the idea, of course, is that if you could solve this problem, right, and you're allowed to pick the threshold t that's part of the input, then you could certainly kind of zero in very quickly on the true product value of x and y by kind of doing binary search on the values of t, right? So you can first ask, is the product at most 100? If the answer is yes, then you might ask, okay, well, is the product at most 50, for example, and you keep cutting things in half, for example, something like this, right? So if you have kind of an upper and a lower bound on your search space, you can kind of keep cutting it in half each time. So with just log overhead, you can solve the actual optimization problem too. So that's why in many ways, decision problems are nice to work with. You can often solve optimization problems given access to an oracle, let's say, solving the decision problem. So now the reverse of this problem, which is not in P, so I don't want to write it under the same heading, but I'm going to use it to motivate NP, right, is factor. Okay, so this is what Schwarz algorithm solves, basically. And again, the integer factorization problem, normally it outputs an integer, not a single bit, but I'm going to write it in decision form so that we can talk about it later on being in this a quantum analog of P. Okay, and this is the following. So given, now the opposite, right? So I'm giving you an input z that's in, it's an integer. Let's just assume it's positive. So it could have been a natural number, of course. And you're also given a threshold t, right? You ask, does z have a non-trivial factor, meaning it shouldn't be 1, less than or equal to t. Okay, so every time, of course, you could ask, does it have a factor smaller than t? And every time you want to find one of the factors, you just kind of do binary search to find the smallest such factor that's non-trivial. And then you could divide z by that, and you could recurse this entire process to really extract out the full prime factorization of z in this way. Okay, so in other words, basically, do there exist integers 1, so x and y? Let me just be a little bit more formal, such that xy equals z. So this is what I mean by a non-trivial factor. Okay, so the factor x over here is strictly larger than 1, right? I don't want 1. Okay, so these are kind of the two problems. Okay, so let's fix this spelling error. These are the two problems we'll use to kind of frame P and NP. So multiply certainly in P. I mean, you learned a grade school algorithm, right? That's exercise 8, actually. A grade school algorithm for multiply that works in polynomial time. So, as a good exercise, think about how you would kind of do that on a Turing machine. Again, use pseudocode, obviously, to do this. And think about the overhead in running that algorithm. And the other reason why I like to really use kind of multiply as our example in P is because it sets up factoring. Okay, so in particular, you've probably all learned about multiply when you're like grade 2 or 3, right? But think about when you actually learned about the factoring problem, right? You probably didn't learn about factoring until much later. Like I learned about it in high school for sure, right? Or maybe like, late grade 7 or grade 8. But certainly I remember learning in high school, and there's a reason for that, right? And the reason is because there is no kind of efficient generic algorithm for factoring, right? We just don't know how to do that thing efficiently for large enough inputs, right? And however, what is known, of course, so this is not known to be in P. Okay, and this is, in fact, what things like RSA and crypto systems are. A lot of crypto systems like, well, the main crypto system I'm aware of course, that works based on factoring is RSA, but I'm not a cryptography expert, if you will. It's not known to be in P, okay, and RSA relies on this, right? But it is, however, it is in NP, right? And what that basically means is that, if you give me the answer, right? If you give me, the factor x, right? So given the factor x, right? I can try to divide my number z, right? So here is my input, right? Z by x in poly time, right? So certainly I can do this. So I can certainly check the answer efficiently. I can check if this is really a proper non-trivial factor you gave me efficiently. Okay. Another kind of well-known example of this is if you do any sort of like hard puzzle game like Sudoku, let's say, right, where you have to fill out this table. Filling out the table itself could be hard, right? It's not clear how to do it. But if I at least write down the solution to the table, it's easy for you to check that it's a valid solution. Okay. So the definition I'm going to give for NP, therefore, is going to be in terms of proof verification. That is not the original definition of NP, right? So the name of NP seems totally misleading with respect to the proof verification view. But for this course, it'll make a lot more sense to think this way, because we're going to generalize this definition for quantum NP, non-deterministic polynomial time. Okay, NP. Okay, and so let me give this definition. It's going to be very similar to the one for P, right? Except we're going to add in basically a proof now, which will be verified, right? Okay, so again, a language L is in NP, right? If there exists a deterministic Turing machine, right, M, and Now I need two fixed polynomials. One is going to specify the runtime, and the other one will specify the proof size. So let me, I'll maybe put in red everything that's new here, right? So this one is new. PL is my new polynomial, and I already had RL from before, right? Let me not rewrite everything out, right? So there are two polynomials such that for any input x, sorry, let me specify the length is important, right? All right, there you go. So for any n-bit input x, m takes in, sorry, this is new, right? Takes in the proof, quote unquote, right? Y. So this is just going to be some string, and the point is that this string is also going to be polynomially bounded, so it's at most PL of n, right? So there's the P coming into play. And then it halts, just like the definition of P, halts in order RL of n steps, and does the following. One. So again, we have completeness, which is the S case. From now on, I'm just going to write completeness because that's a little bit more formal and standard. So if x is in L, right? Now what's new is that now there's a proof in play, right? So if the string is in the language, then you need to be able to give me a proof to convince me of this, right? So there exists a proof Y, and of course the key point is that this proof is polysize. Okay. Such that M accepts, you know, both the input and the proof together, x comma y. Okay. And the no case soundness, if x is not an L, then think about it for a sec. What should be true? If this is going to be a meaningful proof verification system, then if the answer is no, then you should, no matter what proof you give me, you should not be able to convince me that the answer is yes, right? So for all proofs, y M now rejects the input coupled with the proof. Okay. So that's the basic definition of NP. So let me just be clear. Factoring is certainly in NP, right? Because you can just, the proof you would send me y is just the factor that I'm looking for, and I could just verify that it's a factor by just dividing my starting integer by that factor. Again, we did not, we're working in terms of the proof verification view, so we're not really going to talk about non-determinism in kind of the original definition of NP. That's okay for this course. Non-determinism in that kind of view is more closely connected to things like quantum Turing machines, right? So we won't use that kind of view so much. We'll be more talking about quantum circuits, and for quantum circuits, it makes a lot more sense to think about proof verification. Okay, so now I've defined P and NP, and the natural thing to do next is to talk about kind of the canonical kind of NP problem, if you will, at least the hard canonical NP problem, which is the Boolean satisfiability problem. Needs to go. Oh. Undo. All right, the Boolean satisfiability problem. Okay. So, oh, but it also undid that S. Huh. All right, well, that's good enough. So the Boolean satisfiability problem is the canonical NP-complete problem. I'll define NP-complete in a second, of course. And I'm going to focus on it here just a little bit because later on, of course, we're going to define a quantum analog of the Kook-Levin theorem, which I'm also going to talk about today, the classical Kook-Levin theorem. And there'll be a quantum analog of satisfiability, which will turn out to be very physically motivated, right? And that's what we're going to use to prove the quantum Kook-Levin theorem in a few lectures down the road. Okay, so what is this problem? I'm typically going to focus on KSAT, if you will. And in this problem, what is the input? Okay, so by the way, it's always good to get used to writing things formally in terms of input-output. Okay, This holds far beyond theory, right? If you are a coder, you like to code, or you're going to work in a coding job, you should always get used to writing, when you write a function, say in Java or whatever, you should get used to always writing kind of what are the expected inputs and what are the expected outputs of the function, right? The pre and the post conditions in some sense, if you will. So the inputs have to come from a certain class, and this is what you expect of the input, if you will. And assuming the input conditions are satisfied, what are going to be the post conditions of your function? What is going to be the output? Okay, so let's write down the input. The input is going to be a Boolean formula. Phi. Okay, and this is what? It's 0, 1 to the n, and it just outputs 1 bit. And it's going to be in something we call conjunctive normal form. It's not going to make so big of a difference when you get to the quantum setting. Well, there won't be a direct analog of CNF, but still it's worth being clear. Okay, so this is what we have. Okay, so for example, let me just give you an example of something like this. Right, maybe phi looks like this. Doesn't have to look like this, of course. I'll define this notation in a second. x5 bar or x3 and dot, 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 so you've got all these clauses, right? x7 or x4 or x, whatever, it doesn't really matter. Just trying to be consistent with the notes. So perhaps my function phi looks like this. These guys are basically literals. And the word literal as opposed to variable typically means that we distinguish between x and x bar. This bar on top is a negation, it's the NOT gate, right? This v over here is an OR, a bitwise OR, right? And this is the bitwise AND. Okay, and this thing is basically a clause, right? So typically this is a 3-sat formula, let's be clear. Because I have clauses of size 3, you see, so there are 3 variables in each clause, right, or 3 literals in this case. And right, and so to satisfy the formula, to kind of get this Boolean formula to evaluate to 1, you have to, because we have ands between all the clauses, you have to satisfy every single clause individually, right? So that all the ands are true. And so what is the output? The output is the following. Does there exist an assignment x? And we're going to assume that there are n variables in play here, such that phi of x is 1. Okay, and let me be clear, that up here in this formula here, I wrote down like x1, x2. What do I mean by that? Well, I'm assuming x can be broken down into a sequence of bits x1 through xn, right? That's what we're doing here. Okay, so in other words, is x, the name we give to this is, and we'll use it throughout the course, is phi satisfiable? Okay. Okay, so that's the Boolean or the KSAT form problem. It is certainly an NP, right? Because you just give me the string x, its polynomial size and the size of the formula, right? And I can just plug it in and check whether this Boolean function goes to 1. It's not obviously in P because, well, how are you going to come up with that satisfying formula? And, as a very simple exercise, you've certainly thought about this before, but, you can think about a little bit about, why P is in NP and why NP is not necessarily contained in P, right? That's just exercise 13 in the notes, but, let me not focus on that in the lecture. Okay. So now we can talk about the Cook-Levin theorem, NP completeness, and reductions. Okay, so what makes the P versus NP framework so prolific is that it captures many, if not most, practical computing problems, at least decision problems. Okay, so this can range from anything from, solving systems of linear equations, when phrased as a decision problem, to even NP hard things like scheduling on multiple processors. Okay, and really to give you a sense of context, the number of known NP hard problems, numbers in the thousands. Okay, like there's just a huge number of these. Okay, for context, the number of known kind of quantum NP hard problems is much fewer than in the thousands, right? We're probably in the tens at best. I don't think there's even 100 yet. I mean, so it's much smaller, kind of the current scope of it, just to give you a sense of where we are. Okay, now, but of course, let's be clear that the classical setting is a theory that's been developed over 40 years now, right? I mean, so it's modern compared to other fields of study like say physics or math, but computer science, theoretical computer science especially, is a very modern topic. But at the same time, that theory of NP completeness has been developed for 40 years now. And in particular, if we think of like the definitions of P and NP and the classes and the problems they capture is kind of like the Eiffel Tower of complexity theory, then the Arc de Triomphe of complexity theory would in some sense be the Cook-Levin theorem, right? It's a theorem that kind of starts this NP hardness saga, if you will. Okay. And what it basically showed, like what is so amazing about this theorem, right, is that it shows that kind of every problem in NP, doesn't matter which one, they're all equivalent. Essentially, they can all be reduced to one problem, the satisfiability problem. And when you compare this, when you couple this with kind of the Cook-Levin theorem was published, published formally in the early 70s by Stephen Kook in the West and Leonid Levin in the East, basically. And it was Karp's follow-up paper in I think 1972 or at the latest 73 that showed, okay, SAT is say NP complete, Cook-Levin theorem, but really there's so much more to this NP completeness stuff that many long-standing mathematical problems, right? Problems for which people were looking for efficient algorithms for at least a century. Many of these problems could now be shown kind of just inherently intractable. They're also NP complete. That's what Karp shows, basically. And this kind of really kickstarted the theory that showed that this is no kind of esoteric theory. Really, this thing is going to underlie many of the practical problems we see in real life, in everyday computing. Okay, so this is why the theory has really exploded so much in the last 40 years. And to just remind you of the theory of NP completeness and the Cook-Levin theorem, which I won't prove, by the way, in this lecture, but we will review it in a future lecture when we talk about a quantum Cook-Levin theorem. The first thing I'll have to do is just define a reduction. Okay. So a reduction is just basically, intuition. You want to reduce some problem that you don't know how to solve, problem A, to some other problem B that you do know how to solve, right? That's the basically the basic idea. So don't know how to solve. At least intuitively, this is how you should think about it, right? So you know how to solve. So a cute little example in the notes is let's suppose you're a couple of years old. You're just a little kid, right? You're too short to reach the handle for your fridge. You don't know how to solve problem A, opening the handle to your fridge. Okay. How do you solve this problem as a child? Where you reduce it to the problem of getting your parents' attention, right? If you can only get your parents' attention, which would be problem B, then you could tell them open the fridge for me, right? So that's a very intuitive idea of the direction in which this reduction goes. Okay. And in this case, of course, it's the toddler or the child that's kind of computing the reduction, if you will. They realize that I would like to open this fridge, and so they reduce that. They compute a solution, which is to go through the parents, right? And of course, we're going to take our toddler and replace it with a machine, right? With a Turing machine. And I'm going to give you again a formal definition, of reduction, which is as follows. These numbers, I just realized these numbers for the definitions will probably be off in my notes because I updated my notes right before starting this lecture, and so I added exercise numbers for the exercise, and that means that the definition numbers will have changes too. So if you notice mismatches in the definition numbers in the slides, or sorry, on the whiteboard, that's why. Okay, so you should always go by the latest version of the notes. So I'll just say definition, I won't say the number because it won't be correct here. It should be definition 14 if I'm not mistaken. Maybe I'll just put that in because the previous exercise I've marked here should have been 13. Okay, so what is a reduction? So we'll say, imagine I have two languages, A and B. Okay. we'll say that a reduction, and I'll write a subscript b, so we're reducing a to b here. So a reduction from a to b is what? It's a computable function. Okay, so computable just means that it's a function which can be computed by some Turing machine. So given the input, there's a Turing machine which produces the output. So f, right? So it takes in some string, outputs some other string, right? Notice how we don't really put restrictions on the lengths of these strings a priori. Okay, so such that for all inputs, x, so this is the key property, if and only if f of x is in b. Okay, so this is the basic idea that you take your problem in A and you reduce it to some other input f of x to b, such that your original input x is in A if and only if f of x is in b. Okay, and we will say the reduction. So notice how I said nothing in this definition. All I said is that there exists, a computable function, right? Computable says nothing about runtime. So there's just a Turing machine that computes this function. But often, especially for complexity theory where we care about resources, right? We say the reduction is efficient or polynomial time, polytime, if the Turing machine computing the reduction, and in particular this would be the Turing machine f, I suppose, right, is polytime. So let me be clear, is poly the size of x time. Okay, so to be more clear, what that means is there's some fixed polynomial for the entire language, so that no matter for the language A, so that no matter what input x you give me in A, this function f is computed in time, that fixed polynomial in the size of the input time. Okay, and in this case, we would write, A reduces to B again, with the key difference is that we'll put this, this is, I guess, semi-standard. We'll put this P there to say that it's a polynomial time reduction. Okay, and in this course, we'll generally concern ourselves with polynomial time reductions. If you're not asking for polynomial time reductions, then you might be interested in something more general like undecidability, or other concepts too. But in this course, we'll certainly talk about polynomial time. Okay, good. So here's a cute exercise that I just want to very briefly sketch for you. I'm not going to solve it, but I think it's worth thinking about because, again, it will return to your very basic knowledge, like skills you've learned since you were, in elementary school, to think about something formal like a reduction, right? So in elementary school, the first time you learned how to multiply, right? There's a good chance you didn't actually learn multiplication per se, but you learned, like, instead of computing, 3 times 4, you instead took 4 and you added it 3 times, right? You did 4 plus 4 plus 4. That's a reduction, right? That's a reduction from multiplication to addition. Right? You've been doing reduction since you're like 7 years old, right? You just didn't call it a reduction, right? And certainly I'm assuming here you're a polynomial time computer, right? So the overhead in your reduction was polytime. So let's define, let's make this a little bit more formal. Let's define the function add, or the language add, right? Again, I have to make it a decision problem, right? That's another reason why I want to stress this. As the set of, k plus, well, let me not call them k plus 1 tuples, but let's just say tuples, because k is not necessarily fixed. So where you give me k tuples and k numbers, I'm just going to add them, right? And I get a threshold t, and these are just integers. Let me not fix the size because k is allowed to be part of the input. And so these are all the inputs of x1 to xk, such that if you add all these numbers, right, it's at most t, the threshold. So we've turned it into a decision problem, and this exercise says give a reduction from multiply, which we've already defined previously, to add. Okay? So I want you to show me that multiply reduces to add. Okay? And I want you, of course, do it in this formal framework, right? I want you to, what is the output tuple you'd get from multiply, for example, right, to answer this question. So that, x is in A, so that, this tuple is in add, if and only if the tuple you come up with is in multiply, okay? And one of the reasons why I like this exercise is because I want you to think about, once you formalize, these tuples and the sizes that they're going to have when you go through the reduction, the question is it a polynomial time reduction? So I'm going to put a question mark here. Right, so certainly there is a reduction. You've known this forever, right? But I want you to think about whether that reduction is actually a polynomial time reduction. Okay, and as a hint, I want you to think about what it means to be polynomial time, right? When I say something is polynomial time with respect to what, right? We mean with respect to the input size, right? We define Turing machines in this lecture for that reason, right? So you know formally what it means for an algorithm to run in polynomial time. Okay, so think about that when you try and answer this exercise. Good. So let me very briefly mention something, which is that, in this definition up here, this is kind of like the most natural, in some sense, strictest definition of a reduction, right? It's what we might call, definition 14 is what we call a many one, well, sometimes called a Karp reduction, especially if you're talking about a polynomial time many one reduction. Oh, sometimes it's also called a mapping reduction. Okay. Okay, and why is this true? Well, let me sorry. What does that mean? That just basically means like you take a single input of x, right? And you get a single output of b. A single output that you're going to test for b. Right? So what's the idea here is that x is mapped to f of x, and right, x is in A if and only if f of x is in B. Right? So there's this really nice kind of mapping between the two settings, right? You get one input for x, and it gives you one input for B. And of course, this is a little bit restrictive, right? Because in general, maybe you're solving some type of problem where you want to kind of take your starting problem and reduce it to multiple instances of the second problem, okay? And that would be called something called a Turing reduction. So this is versus something called a Turing reduction, which we probably won't focus on too much in this course, but it's certainly worth being aware of, right? And so what we think is that, the view here is that, imagine. I'm going to phrase both let's say Karp reductions or many one reductions and Turing reductions in the same kind of picture now. So imagine we have an oracle or a black box. I'm going to call it OB, right, for deciding the second language B, right? So what many one or mapping reduction does. So what it does is it computes f of x. So given x, it computes f of x, plugs f of x into the oracle for B, outputs OB's answer. Okay? And let me really stress that it's kind of immediate. Okay? So in other words, you can imagine that you run the oracle OB, it gives you an answer. But you might want to kind of post-process this answer. Maybe you want to flip the answers a bit. You're not allowed to do that. Okay, in a Karp reduction, it's literally supposed to be, x was a yes instance if and only if f of x is a yes instance for B. Okay. Now, what happens if you want to do something slightly more general, like take the answer of this oracle, right, and you want to even just do one thing, flip the answer, right? Then you're talking about a Turing reduction. Okay, because then you should be able to call the main difference now. So here's the actual kind of very rough definition. I'm not going to define it formally because we won't focus on it too much. Is and the main idea here is that OB can be called poly many times, and potentially adaptively, right? So, I mean, the first time you call it, you get an answer. You can do some computation, some post-processing. Then you could decide what your next query to the OB oracle will be, and so forth. Followed by, it can be adaptive, post-processing, after each call. Okay, and of course this is if desired, right? I mean, you don't have to do anything if you don't want. So certainly, Turing reductions, generalized mapping reductions, right? They're less restrictive because you could use OB in pretty much any way you like, or you can jump up and down on it if you like. Mapping reductions are very nice and clean, right? You have to play nice with that box. Okay. Now, let me just make a very brief note that the reason why I mentioned Turing versus many one or CARP reductions is because, generally speaking, it's believed that many one reductions and Turing reductions are not the same in computational power. Right? There is formal evidence for that in the classical literature, but I don't want to touch on that here. We do see this showing up in the quantum setting. It's not provable, but as far as we can tell, there's something called the quantum separability problem. Okay, and basically in this problem, we just ask, given a bipartite quantum state. Okay, and when I say given, and I mean I literally write out the matrix for you. This is important. Okay, you want to ask, is row AB entangled? Or technically you want to ask, is it separable? Okay, so is it not entangled? Okay, and this problem, we've known for a very long time now that it's strongly NP-hard under Turing reductions, which means you can take a problem like, say, clique, and using a Turing reduction, you could reduce it to separability, but it's not known to be NP-hard under the stricter notion of mapping reductions. Okay, so it doesn't mean it's not possible. It's just, we don't know how to do it yet. Okay. And, that's been kind of open for at least 15 years now. I do want to mention another nice problem, which is the so-called, this is like, it's really quantum motivated, right? But in some sense, it's a classical problem in that, the input is a matrix, and I want you to determine some kind of algebraic property of that matrix. You can also talk about genuinely quantum problems like the so-called consistency problem, where I give you a bunch of local reduced density matrices, and I ask whether that's consistent with some giant global state. And that also for a very long time, right, since 2006, I think, was only known to be hard for quantum NP under polynomial time Turing reductions. It was only recently, last year, that it was finally shown that it's actually also hard under many one reductions. Okay, so these kind of things certainly tend to pop up in the quantum setting, and it seems kind of difficult to get around them, to resolve them. Okay. Now, let's talk about NP completeness. Okay, so now I have reductions, and now I can define NP hardness, okay, and NP completeness. So you should think about, okay, first let's define NP hardness. Okay, so definition, NP hard, okay. And so what does it mean to say a language is NP hard? Right, so this just basically means that if for all languages A in NP, right, there exists a polytime, so it's got to be efficient, reduction to B. So in other words, this is true, right? Doesn't matter which language I start with A, right? I can always reduce it in polynomial time to some language in B. Okay. So you can think about it if you want. It's not an exercise here, but what happens if the reduction is allowed to be exponential time, right? And so think about it and see if, well, okay, I'll make a claim. I'll claim that, if you throw away this idea that you want reductions to be polynomial time, then you can show, in fact, that NP, well, under exponential time reductions, right, NP is contained in P, okay? Well, okay, that's, I guess, not entirely true, because P can only run in polynomial time. All right, let's not go there. Regardless, we need everything to run in polynomial time, of course, because we want the entire verification procedure, right? So you take A, you reduce in polynomial time to B, and then you can verify B. So it kind of preserves this idea that things can be verified in polynomial time. Okay. And of course, then it would also imply that if you could solve B in polynomial time, then you could solve A in polynomial time. Okay, good. You should think about NP-hard problems as problems which have a lower bound. Okay, so they're at least as hard as NP. So this is kind of like a lower bound on the difficulty of B, right? Here's B. So, if I think about something like NP, right? Let me draw the set. NP is a set of languages, right? Each of which is in turn a set of strings. What we know is that B is, potentially in B. Sorry, it could be somewhere here, right? It's at least as hard as anything in B, but it's also entirely plausible that, you're something much harder, right? It could entirely be that B is out here, right? And maybe, this here is going to be the decidable languages, right? And maybe B is the halting problem, right? It's not even decidable. I dare you, right? You can go ahead and prove, for example, that the halting problem is NP hard. It's at least as hard as NP, right? That's, by the way, a fact. You can actually prove that, okay? It's a serious dare, okay? But it doesn't necessarily mean that, so B is at least as hard as NP. It could be much harder than NP. It doesn't necessarily capture NP in any sense then. And so we also want to talk about not only are you as hard as NP, but you're actually contained in NP itself, right? We need a matching upper bound. And that's what this notion of NP completeness is. It gives you matching upper and lower bounds. Okay. So we say that a language B is NP complete if B is NP hard. So just like before, so that's our lower bound of difficulty. It's at least as hard as anything in NP. And B is actually in NP. Okay, so you're kind of exactly as hard as NP. So if I were to draw this again, here's NP, and here's, for example, here's my decidable set. But this is just saying that B is actually in here as well. And everything in NP can be reduced to B, right? Somehow it's kind of the hardest, if you will. Good. Of course, you don't necessarily have to talk about completeness and hardness and reductions only in the context of P versus NP. You can talk about, you can do this for pretty much any complexity class as long as you define your notions of reduction appropriately. Usually you want your reduction to kind of respect the resources required somehow to solve, the problems of the classes you're interested in. So, for example, if you're trying to do reductions from one problem in P to another problem in P, you might want to make the reduction not polynomial time, because then you can solve the entire problem during the reduction itself, right? That you started with. But instead, maybe you restrict it so that the reduction runs in log space or something. Okay, so polynomial time, but log space. Okay. So, but in this course, generally speaking, we think about polynomial time reductions. Okay. So NP complete problems are the hardest in NP. And when I say a problem is, say, complete for NP, or later we'll say it's complete for quantum NP, QMA, you should think of that problem as kind of characterizing that class. Okay. Okay. Good. So now we get to the Cook-Levin theorem. Okay, and kind of an example of a reduction. Again, I'm not going to prove the Cook-Levin theorem here. I'm just going to state it, and I'll give you simple reduction just to get you get the juices flowing a bit if you think about it, if you want to put it that way. So the Cook-Levin theorem. Okay, and so where does this come from? Basically this shows that SAT is NP complete. Okay, so this is basically by Kook and Levin. And then, right afterwards, Karp uses this to show that, to give a further reduction. There's Karp's 21 NP complete problems, which is NP complete problems, which is, taken together, these papers arguably kind of founded this theory of NP completeness, right? And Karp shows that NP, not just SAT, but 3 SAT is NP complete. Okay, but formally I'm going to write theorem Kook-Levin in the original version is just that SAT. I guess I already wrote it up here. SAT is NP complete. Okay. Good. So I'm just going to assume that in this lecture, we'll talk about the proof later when we generalize it to a quantum setting. But for now, all I'm going to do is I'm going to show you how to start with this assumption, right, that satisfiability is indeed NP complete. And I want to show you basically Karp's reduction that shows that 3 SAT is NP complete. So very simple, very cute, elegant construction. And it kind of demonstrates this idea of a reduction quite nicely. So here's a lemma that, in fact, not just SAT, but 3 SAT, where, remember, this means that your clauses have size 3, right? X2, maybe something like this. Your clauses consist of just 3 variables, right? That was the idea of 3 SAT. And you have this very special form of ors inside a clause and ands between clauses. Whereas generally for SAT, it's just like a formula, and you want to know if you can satisfy it. Okay. Or maybe for SAT, maybe I don't remember exactly, but okay, it could be that SAT you have CNF formulas, but the clauses don't have to be exactly k in size, and then CSP is usually used to determine more general Boolean formula you might want to solve. Okay, but of course we're talking about 3 SAT, so our clauses now are size 3 exactly. Okay, good. Now, how does the reduction go? Okay, so what's the proof? So 3 SAT in NP is trivial, right? We've sort of already sketched this, so I'm not going to go through that, right? You just give me the proof and I just verify it. So, so we show that SAT reduces in polynomial time to 3 SAT, right? And hence, since SAT is NP hard, so is 3 SAT. Okay, and SAT is NP hard, of course, by the Kook-Levin theorem, right? I'm using this assumption here. Good. And good. So how do I set this up, right? So the first thing you should do typically is you should kind of follow this framework when you're doing these reductions, right? Number 1 is first you should actually give me the construction for the reduction. 2, you should make sure you argue why the reduction really runs in polynomial time. 3, you should show the actual reduction is correct, meaning x was in the first language if and only if f of x is in the second language. So let's assume, so we start with some input, right? This is an input, an n-bit input to SAT, right? And what do we do? We construct now a 3 SAT formula, and it's actually going to act on the exact same number of bits. I'll call it psi prime, or phi prime, sorry. It's going to act on the same number of bits, but the number of clauses will change. Okay, such that, and here's the key property, phi is satisfiable if and only if, so this is what I started with, phi prime is satisfiable. Okay, so here's phi prime, and here's phi. Okay, so that's what we're going to do. Okay, so how do we do this? We're just basically going to do this on a kind of a clause-by-clause basis, and I'm just going to sketch the construction. I won't give you the full gory details, though it's pretty simple. So we'll just go clause by clause. I'm just going to take a clause of SAT, right? Which, yeah, okay, I guess indeed it is a CNF formula, right? It's just that the clauses can be very large now. So we'll assume that let C be some arbitrary clause. clause of phi. Okay, and let's suppose it has some size s, whatever s is, right? It doesn't have to be 3. It's going to be at least, I guess, at least 3 in size. So let's just say at least 3, right? Sorry, I guess you want it to be at least 4, right? Because otherwise we've already got to 3, right? Okay, and then let's just write it out. So the clause looks like this, right? So I'm going to use very generic notation. So you've got your first literal L. That's why I have an L here. So it's the clause C, and so I have number 1, right? Or the literal clause, and this is the second variable, or ... or the literal clause, and this is now, I guess, s variables, right? Because I said it's size s. Okay? And these are arbitrary literals, like these LC1 through LCS. They could be anything. They could be like x1 bar, and the other one could be x2, and so forth. Okay, so so we map C to a pair of new clauses. Okay, so what does that mean? That means that I'm going to remove C from my instance, and I'm going to put in 2 new clauses, which capture C, basically. And I'm going to call them C1 and C2 of size s minus 1 and 3, respectively. Okay, so the 2 clauses I come up with, we're going to always shrink the size of the clause by 1. That's this s minus 1. And then we'll have one of size exactly 3, which is what we're going for. Okay. So how do you do this? Well, it's very cute, the trick. For each such variable, every time you do this, you introduce a new variable. Okay, so I guess I misspoke earlier. I said, to be a little bit careful, right? So this is not, so this thing here will change. Sorry. This is a typo. This will change, right? It's not n anymore because I'm introducing new variables, right? So, there's some formula you could work out for how much it's gonna blow up, but certainly it'll be some polynomial overhead, and it will depend on, the number of clauses you have of size bigger than 3, and what exactly their sizes are, right? Okay, so we'll introduce a new variable, yc, good, and define. So the 2 new clauses are what? Well, we're going to have C1 and C2, right? So what I'm going to do is I'm going to take the first L of C, comma 1. Why did I do that? There. Or L of C, comma 2. And ... And now what I'm going to do is I'm going to strip off basically the very last one, right? So meaning I'm only going to go up to, I'm only going to go up to s minus 1. Okay, so you notice here it used to be s, right? I'm not going to go up to s. I'm going to go to s minus 1. I'm going to strip off the last variable. And instead, I'm going to insert this or yc variable. Okay, the new one, right? This is the yc variable right here. And what I'm going to do here is that in the other one, I'm going to, I went a little bit too far, right? I could actually strip off 2 variables. Right, it's more efficient. So I'm going to remove the last 2 variables. So now the size of this clause, by the way, is what? It's s minus 1, right? Because I have s minus 2 terms here, right? And then I have the new variable I added. Okay, and what about this one? Well, this one will be the 2 variables I stripped off. Now they'll be here. So here's your s minus 1. Here's your s and your s. Those are the last 2. And now it has to be size of at least 3. Well, it doesn't have to be, but it's going to be in order for this reduction to work. Now I put in this yc, but I'm going to do something slightly different, which is I'm going to negate yc here. Okay, and here's your size 3. Okay, and that's what I said, right? I said up here, size s minus 1, size 3, and there you go. Okay. And so this is the entire reduction. I mean, you kind of repeat this over and over again, right? So long as you have a clause of size at least 4, you apply this reduction to 2 smaller clauses by introducing a new variable. And I mean, you can convince yourself by staring at this long enough that this is certainly going to be polynomial time. And I'm not going to spend the time to go into it. But you can count the number of times this will happen. It will certainly be time polynomial in the size of the input. And for correctness, I'm going to leave that as an exercise, actually. I think it's a nice exercise, but it's not very complicated. I mean, you could just stare at this long enough. And the key idea is, of course, what that I claim that. Now, well, here's the claim. I mean, to prove correctness, you would prove the following, right? Formally, the claim is the following, that C1 and C2 is satisfiable if and only if C is satisfiable. Right? That's really what you want to show. And of course, the way you see this is you have to look at this auxiliary variable, right? It takes values in 0, 1, right? It's a Boolean variable. So, if it's 0, that means that one of these will be false, right? So say the value is 0 of yc, then this guy here is false. Then you would kind of cross this one out because it would go to 0. And that means that the only way to satisfy this clause now is you have to satisfy one of these variables in front, right? Oops. Okay. And conversely, if yc is 1, well, in that case, then, you'd play the same game, but with the other clause, right? Then this one would, if yc was 1, this would go to 0, basically, because it's a negation. And then you'd have to satisfy one of these two, right? So regardless of the setting of yc, you're going to have to satisfy either this part of the clause or this part of the clause, of the original clause, C. And these two parts were originally linked with an OR, right? Everything is an OR. It's a SAT formula. And so that completely captures the original clause in this sense. Okay? But I'll let you kind of write that down formally. And let's see. And here's a cute exercise, which I'll give to you. Okay, just to practice a little bit more in terms of doing reductions, right? So prove that 3-sat is NP-hard, even if each variable appears at most 3 times. Okay. So, this reduction up here, what we did is that we kind of shrunk the size of the clause down, but, variables can potentially show up multiple times, right? And here I want to say, okay, well, even if each variable shows up a very small number of times, a constant number of times, it still is an NP-hard problem. Okay, so I'll let you think about that. Kind of the hint is to try and think about what it means to set 2 variables to be equal to one another. Okay. And with that said, we can move to the closing section of today's opening lecture, if you will, which is we can return to what we started with, this discussion of the so-called crossroads complexity theory, is that, and this extended church Turing thesis. That's probably the most straight line I'm going to draw all term. Okay. Okay, so due to Schwarz factoring algorithm, okay, which is a polynomial time quantum algorithm for solving the problem factor, which we talked about today, one of the following is false. Okay, there's a slight caveat. This is not a fully rigorous statement. I'll mention that in a second towards the end. But let me just rewrite these statements now. So the extended church Turing thesis is true. Okay. Factor is not in P. Okay. And large-scale quantum computers can be built. Okay, I claim that, at least kind of intuitively, this implies that one of these must be false. Okay, we have to be a little bit careful how we phrase some of these things, and in particular, this, how do we compare the first 2 points to the third one, and I'll say more in a second. Before I do that, though, let me just briefly define for you the extended church Turing thesis. Right? Remember that the regular church Turing thesis just says that if there is a mechanical process which computes some function, then there's a Turing machine that also computes the same function, right? It says nothing about the overhead, though, that the Turing machine needs to do that simulation of the mechanical process. So you might want something stronger. Maybe you want to say that really Turing machines are really powerful. They can simulate everything kind of nature allows in polynomial time. Okay, sorry, not in polynomial time, sorry, with polynomial overhead, right? Okay, and that's essentially the extended Church-Turing thesis, which basically would say the following, right? So any kind of reasonable, or I'll use the words physically realizable, model of computing. And of course, I say physically realizable because the mechanical process I start with for this thesis, it shouldn't be some mumbo jumbo I just kind of made up on the spot, right? That's okay, in principle it's possible, but no, it'd be actually in practice it'd be impossible to actually build this thing, right? That's just silly, right? We don't want to consider those types of models. We really want to consider computing models which can be physically realized using the laws of nature, right? So that's why we have this kind of precondition now, right? So any physically realizable model of computing can be simulated by a Turing machine with Poly overhead. Okay, so there's kind of this extended Church-Turing thesis. That's what that is. Okay, and now the claim is that all three of these statements over here, 1, 2, 3, cannot hold simultaneously. Okay, if any two of them are true, the third one would have to be false. Okay, so let's think about it this way. For example, let's say, for example, kind of the best case scenario. Best case, right? We assume 2 and 3. And this would imply that 1 is false. Okay, so if 3 is true, I can build a large-scale quantum computer, meaning I can solve factoring quantumly. 2 is true, meaning a classical computer cannot solve factoring efficiently. Then certainly the extended Church-Turing thesis is false, right? Because here's a problem that explicitly cannot be solved classically, but can be solved quantumly, right? So it's not true that a Turing machine, a classical deterministic Turing machine, can simulate any physically realizable model with Poly overhead. And I also want to mention the so-called worst case, right? Which is that what happens if you do 1 and 2, right? Okay. And so imagine now, for example, that the extended Church-Turing thesis is true, right? Factoring is not in P, right? Well, if factoring is not in P, then the Church-Turing thesis says that if there's some other model of computing that can solve this thing efficiently, then so can a classical computer. It would also be in P, right? So this is enough to conclude that on any kind of physically realizable model, you cannot solve factoring efficiently, right? And so that would mean that here we have a problem now, because in theory, mathematically, we have a well-accepted proof and algorithm, right, that a quantum computer could factor any integer of length n in poly n time on a quantum computer, right? So the only kind of hole potentially left is that, well, it might be that in practice we just cannot build these machines on a large scale. Okay, maybe, I don't know, the energy requirements turn out to be too big, let's say, or maybe the noise in the system turns out to be too difficult to handle, right? There's nothing in quantum physics which says large-scale quantum computers cannot be built, right? So there's no reason to believe that a priori, but it's always a possibility, right? Okay, and in some sense that's kind of like the worst case scenario for a quantum computer. Nevertheless, let me really mention that, and this will also tie into the last kind of asterisk I want to put on this point here, which is that, so first, even if we can never build large-scale universal quantum computers, and sorry, let me be clear here that I'm typically talking about universal quantum computers, meaning a quantum computer which acts like your laptop, right? You give it a software program, and you could always run that software program, basically, right? So it's universal in that sense. And it could kind of simulate anything another quantum computer could do with Poly overhead. And so even if we cannot build large-scale universal quantum computers, of course, that does not stop us from building kind of purpose-built quantum devices, right, that still do something very interesting, right? And so that's actually already been happening for almost 2 decades now, right? I mean, there are companies out there like ID Quantique that build quantum key distribution devices for quantum cryptography. They've been doing this since the early 2000s, as far as I know, right? And those are not universal quantum computers. They're very special purpose devices that do one thing and they do it well, right? The other thing is that, even if in the worst case, absolute worst case disaster, right, quantum computers just turn out not to be buildable, feasible on a large scale, there's still a lot that has come out of the study of quantum computing as a whole, right? And so, for example, many phenomena in quantum physics, such as entanglement, were very poorly understood for on the order of 70 years or so, roughly. And it's only with the advent of things like quantum information that we've really understood a lot better what it means, what these phenomena mean, and how one can harness them. And there've even been really interesting connections between things like quantum complexity theory and black holes and things like this, which personally I'm not qualified in any sense to speak about, so I'll leave it at that. But certainly you can go look this stuff up. It's very interesting. And so we've learned a lot in terms of theoretical physics just through the lens of quantum computation. So that positive will always be there, no matter what happens with the actual building aspect of it. Good. The last thing I want to close with now is the star I put here. Right? Why in the world did I put a star here? Well, the statement I'm making here in this section, the argument is not entirely watertight, right? And the reason why is because, these first 2 points, 1 and 2, right? These are both in the asymptotic limit, right? We're talking about computing models like, say, P or the extended Church-Turing thesis, where, you're talking about what happens when the input size goes to infinity in some sense, right? It's highly theoretical. The third one is kind of the opposite of that, right? It's not highly theoretical in some sense, right? You're talking about building actual devices in practice. And any such device, of course, is going to have finite size in some sense. And it's entirely possible that, for super gigantic input sizes, right? We cannot scale up constructions of quantum computers to 10 gazillion bit inputs, let's say. And so maybe that's why, theoretically, it would be true, potentially, that large-scale quantum computers cannot be built. But maybe for any sort of reasonable size input, say a couple of thousands of bits or millions of bits or whatever, you can still build a large enough quantum computer to run, okay? That runs. So that's why there's a bit of a star here, right? Because you've got a bit of a disconnect between the first two statements, which are highly theoretical in the asymptotic limit, and the third one is trying to say something more about kind of practical computing and what you can actually do on finite sizes, right? Bounded sizes. So you have to be a little bit careful. It's always plausible that kind of the impossibility of number 3 only shows up, for example, when input sizes are just absolutely ginormous and nobody in their right minds cares about inputs of that size. Possible, right? Anyway, but certainly the intuition behind this kind of this rub between 1 and 2 versus 3 is certainly there. Okay, good. So that's it. So congratulations, you've sat through your first lecture of quantum complexity theory. There, again, will not be a tutorial this week. The tutorials will start in the 3rd week. And other than that, please have a great week and stay posted to the course website and Panda for any announcements regarding things like assignments and so forth. All right, lecture notes are up again. Go to the course webpage. Do make sure you download the latest version and follow those. Good. I strongly recommend, by the way, you read those. They will improve your understanding of the lectures greatly as you go through. All right, have a good week. And as always, during these COVID times, stay healthy.